This is your presenter Asloob Mudassar, and I am presenting slide number 28 of the course on laser physics. Question is, find an expression for the spontaneous emission lifetime or equivalently the radiative lifetime of level 2 in a two-level atom. Answer is, according to classical electrodynamics, an oscillating atomic dipole moment must radiate power into the surrounding space. Spontaneous or the radiative emission is in fact due to this radiated power. The radiated power based on classical electrodynamics approach is given by PR is equal to N into mu naught square omega naught raised to power 4 divided by 12 pi epsilon naught into C cube as given in equation number 1, where mu naught mod square is equal to mu naught square is equal to the square of 2 into mod of A1 A2 star mu 2 1, that is equal to 4 into A1 mod square into A2 mod square into mod square of mu 2 1, and omega naught raised to power 4 is equal to 16 pi to the power 4 and mu naught to the power 4, and N is the refractive index of the surrounding medium. The radiated power becomes PR is equal to PR prime into A1 mod square into A2 mod square as given in equation number 2. Sometimes I am using some expressions directly. For example, I am using here mu naught square, directly the value of a mu naught square. And when I am using these values directly, it means that these values have been taken from one of the previous slides. So have a look at my previous slides to see the derivations of these expressions. So we have at the end in equation number 2 the radiated power PR is equal to PR prime into A1 mod square into A2 mod square, where PR prime is given by PR prime is equal to 16 n pi to the power 3 mu 2 square of mu 2 1 mod square of mu 2 1 into mu naught raised to power 4 and whole divided by 3 epsilon naught c to the power 3 as given in equation number 3. The energy decay rate from the atom is equal to the radiated power, that is dE over dt is equal to minus PR. But you know that we don't have the value of dE over dt. So here we first would like to find the value of dE over dt, and then we shall plug in the values in this expression to find out the expression for the radiated power. To find dE over dt, we proceed as given below. The states of an atom can be written as the superposition of an atom in state 1 and in state 2. Again, for this expression you can see the slide number 27. So now I am writing it in the ket notation. So psi is equal to, in the ket notation, is equal to A1 into psi 1 and then psi 2. The second expression is in the ket notation. So I am operating with the H operator. The Hamiltonian operator has been operated in the third expression, and then we have multiplied from the left by the bra vector, by the bra expression. So we have at the end, you see that bra and ket notation has been used, and then you notice that we have A1 mod square over here and then A2 mod square over here, because we have multiplied it with the bra vector of psi. So then you see that this that is within the bracket we have psi into psi H bar operating on psi. This can be written as the total energy of the atom, that is can be written as capital E, and the other one is the energy of the atom in state 1, which is E1, and the third bracket is the energy of the atom in state 2. So we have written the energy expression, that is E is equal to A1 mod square into E1 plus A2 mod square into E2, where A1 mod square and A2 mod square will give you the probabilities of the state 1 and state 2 being occupied respectively. Now we can express this expression in terms of A2 mod square only. So we can write the last expression can be written as E is equal to the A1 mod square can be written as 1 minus A2 mod square, because the total probability, that is A1 mod square plus A2 mod square, is equal to 1. So using that expression I have replaced A1 mod square by 1 minus A2 mod square. And then you can separate out the coefficients of the A2 mod square as given in the middle expression, that is E1 plus E2 minus E1 into A2 mod square, and E1 E2 can be replaced by H nu naught. So the last expression on the right hand side is E1 plus H nu naught into A2 mod square as given in the last expression of equation number 28.5. So we have the energy expression, because the energy expression is needed in equation number 28.4. The differential using the equation 28.4 becomes, so we are taking the time derivative of dE. So the time derivative of dE is given over here, that is dE over dt is equal to 0, because the time derivative of E1 is equal to 0, plus H nu naught into the time derivative of A2 mod square. And then we have set that one is equal to minus PR from equation number 28.4. So we have minus PR over here. And then we can write this expression in more elaborated form as given. So we have H nu naught into the time derivative of A2 mod square is equal to minus PR prime into A1 mod square into A2 mod square. The expression of PR replacing in terms of a PR prime has been taken from this expression, that is from the equation number 28.2. Okay, so again I am replacing A1 mod square by 1 minus A2 mod square, and then rearranging the term, I have the time derivative of A2 mod square is equal to minus 1 over tau sp, and within the bracket I have 1 minus A2 mod square into A2 mod square. So I have all the terms in terms of A2 mod square, and this tau sp was substituted by tau sp is equal to H nu naught over PR prime, and the value, and substituting the value of a PR prime from this expression, that is from 28.3 over here. Then we have the total expression for the tau sp is equal to H nu naught over PR prime is equal to 3 epsilon naught c to the power 3 h divided by 16 into n into pi to the power 3, and then mod square of mu to 1 and nu naught cube. So this tau sp is actually known as the spontaneous emission or radiative lifetime of level 2, because we have the expression of A2 over here, you see. So we have used in this that is in equation number 28.6 we have A2 mod square everywhere, and then we have the tau sp. So this is known as the spontaneous emission or the radiative lifetime of level 2. This is the end of slide number 28.